Jnanam paramam dhyayam. Knowledge is supreme.
Now, what is the advantage of doing all this kind of thing? Why I am bothering and doing such kind of a thing? You can ask a question. It's nice, it looks nice, right, mathematically, but why one should bother about it? See, look, supposing A is a matrix, for that matrix that we have taken, minus 5, right, minus 5, minus 7 and 2 and 4. Suppose I want to compute the 100th power of that matrix. Right. So, that was the matrix. What was the matrix we had? A was the matrix which we had minus 5, what was the minus 7? Minus 7, 2 and 4, right. This was say, and for this matrix A, I have got P inverse AP equal to 2, 0, 0, 3. There exists P such that this holds, right. I want to compute what is A raised to power 100, right. So, from here what is A equal to? I can write A equal to, from this equation. So, that is A equal to 2, 0, 0, 3. On the right I multiplied by inverse. So, P inverse, and here I multiply by P. Is it okay? So, A is equal to this. So, what is A 100? That is P, this matrix 2, 0, 0, 3, P inverse, whole thing raised to power 100. And what is this equal to? Looks surprising, no? What is it equal to? Let us compute it for square first of all, and then you will see what is happening. So, let us look at P 2, 0, 0, 3. P inverse square. So, what is that equal to? P, this matrix P inverse multiply by itself, right. So, what is it? P inverse. What is that? So, what I get? P this square P inverse. This is 2, 0, 0, 3. What is the square of this? It is 2 square 3 square 0 0, right. So, what will be P to the power 100, what will be A to the power 100? That will be P 2 to the power 100, 0 0, 3 to the power 100, P inverse. See, the computation of the powers of a matrix become very easy, because that is a diagonal matrix now on the right hand side, and for which powers are very easy to compute, and multiplying by, I have to only find out what is P and what is P inverse, only two matrices, actually only one matrix and its inverse, right. So, such a result is what is called diagonalizability of a matrix A. So, what we have done is, given a matrix A, which was our special one, we have said we can find a matrix P which is invertible, such that P inverse AP is a diagonal matrix. The diagonal matrix is known, the matrix P is also known, right. So, the question comes, for what kind of matrices one can do that, right. For this particular one we are able to do it, but we may not be that lucky. So, we have to find a condition which ensures if this matrix satisfies this property, then it can be diagonalized. Not only it can be diagonalized, that means I can find a matrix P such that P inverse AP will be diagonal, and I know what is the diagonal matrix also, right. So, those are the scalars which are going to appear on the diagonal are nothing but determinant of A minus lambda I equal to 0, solution of that, right. So, it becomes important to solve determinant of A minus lambda I, right. So, let us write that as a definition. Okay. So, these are the questions. So, let us a lambda is called an eigenvalue. So, such a scalar is called an eigenvalue if there exists a non-zero vector. Oh gosh, is a typo. There is a vector x such that Ax is equal to lambda x. So, if there is a non-zero vector which is scaled by that vector by the matrix A, then that is called an eigenvalue for, and this vector is called an eigenvector for that eigenvalue. It is called a eigenvector, and just now I said for a given eigenvalue, in this example, the previous example, eigenvalue is there too, but there are many eigenvectors possible for it, right. If one is an eigenvector, scalar multiple of that also is a eigenvector, right, for the same eigenvalue. So, there could be more than one. Actually, you can put them all together in one box, right. You can call it as eigen subspace of with respect to that eigenvalue. So, we will come to that slowly. So, that is called an eigenvector. So, the problem is, this is what is called the eigenvalue problem. Okay, we call it that given a matrix A, find its eigenvalues and find corresponding eigenvectors, right. Actually, the process is quite clear. There is nothing, we have already done one example of that. So, what is the process? Take the matrix A, it is a square matrix, look at for a scalar lambda, look at A minus lambda I, because you want Ax is equal to lambda x. So, look at A minus lambda I, that matrix you want a non-zero solution for that, right. With that matrix as a coefficient matrix, A minus lambda I applied to x equal to 0 for a non-zero x, you want a non-zero x. That means, you are looking for a non-zero solution for the homogeneous system, and that is true if and only if the matrix is not invertible, right. Nullity should be at least bigger than or equal to 1, right. The rank should not be full, that means the matrix should not be invertible, and in terms of determinant, that says determinant of A minus lambda I should be equal to 0, right. So, let us give that determinant of A minus lambda I also a name. Okay. So, that is called the characteristic polynomial of the matrix. Given a matrix A, look at determinant of A minus. So, what will be A minus lambda? Along the diagonal you subtract lambda, right, everything else remains as it is. So, determinant of this, what it will look like? Try to sort of expand. See, in the example 2 by 2, it was a quadratic. In 2 by 2, it came out as a quadratic, lambda square minus, right, the whatever that was. So, here let us say, suppose you expand by this, right, you expand by first column, say. So, this will be gone and this will be gone. So, you will have A11 minus lambda into determinant of the remaining, right. So, when you write determinant of the remaining, again you will have to expand by that. Let us again expand by this column, then it will be A22 minus lambda coming out as a factor into determinant of the remaining one. So, what will be the highest power of lambda that will come? Lambda to the power n, right, plus some lower powers plus some lower. So, essentially we are not exactly proving it, but giving you a hint that intuitive way of saying that this determinant is a polynomial in lambda, is a polynomial in lambda of degree n. So, the characteristic polynomial is a polynomial, that is why it is called a characteristic polynomial, because it actually turns out to be a polynomial, and it is characteristic of that matrix, right. It is a property of the matrix, determinant A1 is a polynomial of degree n, and what will be the coefficient of the highest term? Lambda to the power n, it will be minus lambda, minus lambda, minus lambda, it will be minus 1 to the power n, that factor will come out anyway, right. So, it will be lambda 1 to the power n into lambda n plus something something equal to 0, right. If you want, so problem is how to solve that polynomial, find the roots of that polynomial. These are the values which are going to be called as the eigenvalues of the matrix. right. So, let us look at this. So, the roots of this are the eigenvalues, right. Roots of the characteristic polynomial are the eigenvalues. Now, here is a theorem in algebra called fundamental theorem of algebra, which says here the coefficients are all going to be real, right. We are looking at real matrices, but the roots of a real polynomial need not be always real, they can be complex, right. So, the characteristic polynomial will be a polynomial with real coefficients, it may not have any real root, right, all the roots may be complex. So, eigenvalue need not exist, that is a possibility. So, for a given matrix the eigenvalue, no eigenvalue may exist. So, gone case, for that you can do nothing, you cannot diagonalize that matrix at all, you are gone at the first step itself. It may have eigenvalues, right, some of the roots may be real, some of the roots may be complex. How many all will be there total? This is a polynomial of degree n. So, fundamental theorem of algebra says there will be n roots for this, some of them may be real, some may be complex, but the complex roots always occur in pairs, right. So, if it is a polynomial, if the matrix n is of odd order, then at least one real root will exist, right. So, then a hope is there, you start with that at least. Okay. So, that is coming from algebra basically. Okay. So, let us will slowly come to, so a root, there is something called the multiplicity. If a root is repeated, right, then we how many times it is repeated, that is called the multiplicity of that root. So, eigenvalue may or may not exist, it may exist with some multiplicity, that are possibilities. So, let us look at this matrix, looks slightly okay. If you calculate it, I think this is just example just to show you computation. Determinant of this, you get lambda equal to 2. Okay. How do you get for a cubic? How do you solve a cubic? Even for a 3 by 3 matrix, finding roots is not an easy job. There is no definite algorithm like for a quadratic. For a quadratic, you know, b square minus 4ac divided by that gives you all the roots, real or complex, whatever it is. For a quadratic, for a cubic, one does not know. So, the hope is you find one by hook or crook, divide by that and get a quadratic and try to solve it, kind of thing. For 4th degree, there is no hope at all, right. It is very difficult to find roots of a polynomial. Okay. But here anyway, for this, by just looking at it, you can see that there is a possibility of saying that there is a root lambda equal to 2. Sometimes while you can look at 1 minus 1, 2 minus 2 and some 1. This is for just the sake of examples, nothing more, right. In life, in mathematics life, it is not easy to find roots of a cubic even, it can be tricky, right. So, here you find 2 is a root and all other roots are negative. So, probably one should, let us look at only for 2 what is the eigenvalue, eigenvalue 2 what is the. So, I am just giving a process for lambda equal to 2 to find an eigenvector. This will do for all eigenvalues, a minus 2i applied to a vector x is equal to 0. So, apply that, you get the homogeneous vector, right, homogeneous system. So, how do you solve? Reduce this to the row echelon form, right, reduce it to row echelon form. So, you get this, right. You see, all along in all our course till now, the only one idea which is important. What is the single most important idea? Given a matrix, find its row echelon form, find its reduced row echelon form. Everything comes back to that, right. Everything gets related in that, because that is the way you will compute things on machines. Okay. So, find this. So, that means what? If this is equal to c, so what you get? X, y, z, you solve it, right. This decimal you can remove. So, you get 25z. Z is arbitrary. There is one row which is, right, rank is less. One row is 0. So, what is that? what is the variable you will get an arbitrary value? The third one, z, right. You give z arbitrary value, you find x2 in terms of x, y, z. So, find y in terms of z from this equation, put back the value, you get the value of x. So, comes out equal to this. So, you can take z out, okay. So, that is a scalar, okay. So, times 25, 5 and 1. So, that is an eigenvector for the eigenvalue, okay. So, the eigenvalue for lambda equal to 2 is, this is an eigenvector. So, it is clear how to find eigenvalues and eigenvectors corresponding to that, solve the characteristic polynomial, and for each root solve the corresponding homogeneous system, okay. Here is roots of, see what is determinant of A is same as determinant of A transpose, right. So, finding the characteristic polynomial for A is same as finding characteristic polynomial for A transpose. Eigenvalues will be same, but eigenvectors may not be same for both, because you will be taking A minus lambda I or A transpose minus lambda, that will change. So, for computation of eigenvalues you can replace A by A transpose if you want. So, here is one example of that. So, look at this matrix, okay. Some funny looking matrix looks. We want to find a matrix, a vector u, so that u times b equal to u. What does that mean? It does not seem to be related with eigenvalue, right. But supposing you take transpose of this equation, what you will get? B transpose applied to u transpose is equal to u transpose. That means, for B transpose you are saying that for an eigenvalue equal to 1, find an eigenvector that will be u transpose. Is it okay? Once you have found u transpose, you can find u. Is it okay? So, that is the idea of application of that. So, B applied to, here is some observation which is not really important, but for this matrix, if you look at the transpose of this, so what is the sum of the rows of this matrix? 8.1.1, that is 1. Sum of the rows is equal to 1. So, if you take transpose, sum of the columns is equal to 1. Such matrices are called stochastic matrices, whose columns, each column add up to 1. They basically arise in probability theory, statistics, statistical analysis, because the probabilities are distributed. See, total equal to 1 essentially is something like there are probability of something happening kind of thing, and you want to, this is called the stochastic matrix because it describes the system in probability, and there you would like to know if you apply that process again and again what happens. So, you will be required to compute the powers of that matrix, and that is why for such a matrix diagonalizability becomes important. When can you diagonalize? And one shows a theorem that for a stochastic matrix, number 1 is always an eigenvalue. That can be proved as a theorem, we will not bother about that. So, here 1 is an eigenvalue, so you look at B transpose, so B transpose minus 1 I V equal to 0, solve that system, right, solve that system. So, that will give you the vector V, and what is that vector V? That is the transpose of the vector u that you are looking for, right. So, this was basically just brought in to say that for determinant of A is same as determinant of A transpose, that can be used in finding eigenvalues of the matrix. Okay. So, that is what you find, solve that computation, and you find you can choose, and you, if you want a unit vector, you can, this is an eigenvector, right, 0.2, 0.41. Okay. If you do not want decimals, you can multiply everything by 5, that also is an eigenvector. So, you can 1, 2, 5, you can normalize that if you want. So, you can have a normalized eigenvector, which is non-zero anyway, divide by the norm, you will get a eigenvector of length 1, right. and this is what is important. You go on applying, there is something called equilibrium of a stochastic system, and after some stage it does not change the system at all, you have reached equilibrium in probability theory. So, let us not bother this line. Okay. So, important thing is for the eigenvalue lambda equal to 2, eigenvalue lambda equal to 1 for a stochastic matrix, you can find the eigenvector. So, this has importance in other subjects. So, basically let me summarize. Finding characteristic polynomial and its roots, eigenvalue problem is basically find characteristic polynomial, find its roots, find eigenvectors by solving the resulting singular homogeneous system, right. That is, so as I said, you can put them all together in one box, the null space of A minus lambda I, that depends on lambda eigenvalue, that is null space of this matrix. You can also call it as an eigen subspace, right, a vector space subspace corresponding to the eigenvalue lambda. Now, here is something which probably will bother next time. You see, given even if a lambda and eigenvalue exists, there is an eigenvalue, that means you have to find an eigenvector for that real. But sometimes one allows even complex eigenvalues, the complex roots which are coming for the characteristic polynomial, even one takes into account that there are, then the corresponding matrix that you will get the solution A minus lambda I, then you do not restrict yourself to real entries, your entries will change to complex also, right. So, you may get a vector x which is a complex vector mean, but entries are complex numbers, right. So, instead of looking at matrices over reals, one starts looking at matrices over complex numbers also, because it is forced by that problem eigenvalue problem, right. So, we will start looking at this next time more, we will stop it.